Hello and welcome you all to this lecture. Here we will be discussing about Laplace transformation or Laplace transform. So this is one of the important type of transformation what we have in our syllabus. So Laplace transformation, basically let me write down the definition for Laplace transform of a function ft, okay, which is nothing but integral 0 to infinity e power minus st ft dt. This is the direct definition of Laplace transform. We usually use the notation Fs to represent this one, provided the integral exist. Now for this, provided this integral exists, for this we have some sufficient condition that we'll discuss later on. Now see the definition itself. Laplace transform of a function ft, it is given by some improper integral where the range it is from 0 to infinity, the range of the integral 0 to infinity e power minus st ft dt, and here t is always greater or equals to 0. Now this is the Laplace transformation, and here you can observe this thing. This is given as e power minus st. This is usually k s comma t, which is known as kernel of the integral kernel. Now based on the nature of kst, we have different transformation. When it is e power minus st, and here s can be real or complex, no restriction, okay. S can be real or complex number, okay. So based on the nature of this kernel, we have the different type of transformation. So here we are particularly studying Laplace transformation, okay. So when I am writing L of f of t, that means here t is the variable, and when I am writing s, okay, f of s, now s is the variable. Or see here, this is in time domain, and here it is fs in the frequency domain, okay, frequency domain. Now basically what we are doing, from time domain to the frequency domain, we are shifting our problem from time domain to frequency domain. Now there are many advantages because of which we are studying this Laplace transformation. Now the advantages are, the first advantage is to convert or to solve initial value problem, without finding the general solution, or in other words you can say without solving corresponding homogeneous equation, okay. That means this is the biggest advantage of Laplace transformation. That means without solving the homogeneous equation. That means it is a lengthy process to find solution of homogeneous equation and then particular integral, and finding this general solution means it is a laborious task. So this Laplace transform, we'll learn how we can apply this process. This Laplace transform directly give you the solution, that means the particular solution for a given IVP, okay. So this is the biggest advantage of having Laplace transformation. Now second thing is what? Second thing is Laplace transform solve Laplace transform LT, we can use this short notion. Laplace transform this solves non-homogeneous differential equation without necessity of first solving the corresponding homogeneous differential equation. That's what here already we have written. Okay, next, some problems you will find very tough to solve in time domain problem. Okay, so those problem can be shifted to the frequency domain. Okay, time domain to frequency domain, where one can easily solve those questions, okay, or those problems which are tough to deal in time domain, but they are sometimes very easy to solve in frequency domain. So this is one of the biggest advantage. And another advantage is this Laplace transformation, it is not only applicable for the continuous function, but we can apply this Laplace transformation in piecewise continuous function as well. This is not only for continuous functions, but can be applicable to piecewise continuous functions. Okay. So these are few direct advantage of having Laplace transformation. Now we'll see when we solve question, and that time these things will get more elaborate to all of you. Okay, so this is the basic definition of Laplace transformation, and here we have the formula of Laplace transformation, this one, and these are few advantages of having Laplace transformation. Now we are moving to the next part, that means Laplace transform. If I give you few examples, what are examples? Basic example. Okay, so if the first one is find Laplace transform of, suppose ft is equals to k is constant, k is some constant. So see the process how one can find Laplace transformation. Laplace transform of ft is 0 to infinity e power minus st ft means k, here you have dt. So if you solve this one, k integral 0 to infinity e power minus st dt. So here k e power minus st by minus s with 0 to infinity, put upper and lower limit, and you will be getting k by s. Okay, k by s. So Laplace transform of this ft is this one. Okay, so if k is equals to 1, remark, if k is equals to 1, then Laplace transform of 1 is what? 1 by s. Laplace transform of 1 is 1 by s. Alright, so I got this point that Laplace transform of 1 is 1 by s. Suppose Laplace transform of ft is equals to, suppose t power b, I want this. Okay, so see the solution, Laplace transform of t power b, this one. So integral 0 to infinity e power minus st t power b ds, this one. So here this is an improper integral, so one can substitute st is equals to u. So here obviously dt present. Okay, so here s dt is du, so dt is what? Du by s. So you can substitute this one, limit will be 0 to infinity e power minus u, in place of t you are going to write u by s is equals to t. So here u by s whole power b, here du by s. So if you further simplify this one, what you have, 0 to infinity e power minus u power b by s power b plus 1 du. So here what you have, 1 by s power b plus 1 integral 0 to infinity e power minus u power, this one can be written as b plus 1 minus 1 du. Now you just remember what is gamma function. This is the form of gamma function. You have integral 0 to infinity e power minus x power m minus 1, that is gamma m. So immediately what you can write here, that from here 1 by s power b plus 1, here you have gamma b plus 1. Now gamma b plus 1 is, but you can keep this one gamma b plus 1 divided by s power b plus 1. So this is nothing but Laplace transform. This is nothing but Laplace transform of t power b Okay, so Laplace transform. So from here we got Laplace transform of t power b is what, gamma b plus 1 by s power b plus 1. This is another important result we have. Okay, now if b is an integer, so immediately what we have, this b plus 1 gamma, it is nothing but b factorial. If b is an integer, so immediately what you have, this formula reduces to b factorial divided by s power b plus 1. Okay, so these are few important formulas we are having right now. So you have to remember these formulas in the form of table. Okay, so this is another formula, this one Laplace transform of 1, this is another formula. So these formulas you will find in terms of table in the subsequent classes. Now another function, if I give, suppose Laplace transform of, moving to the next slide. Okay, so another function, if I consider, suppose find Laplace transform of the function, it is given as, suppose ft with 0 when 0 less than t less than 1, t when 1 less than t less than 4, and 0 when t is greater than 4. If you have this type of function, so how to deal with this? Solution. So Laplace transform of ft, here you have 0 to infinity e power minus st ft dt. Now see, there is one condition of Laplace transformation, we'll study that thing also, which says that it is applicable for piecewise continuous function. The same thing already we studied in the advantage of Laplace transform in the last slide, it was there. So here piecewise function means you can break this one, 0 to 1 e power minus st, and in 0 to 1 what is the value here? See, 0, so 0 dt plus 1 to 4 e power minus st, here you have t dt plus 4 to infinity e power minus st 0 dt. Okay, first and third component will give you 0, so immediately you can have this one, 1 to 4 e power minus st t dt. Okay, now if you perform this integration, that means integral t e power minus st dt, so here you have but t e power minus st by minus s minus integral d dt of dt integral e power minus st dt. Okay, integration by parts, we are using integration by parts. It was there in 12th standard, 11th standard. Okay, So if you just do this, t e power minus st by s, here you have minus, from this part you will get minus 1 by minus s, so 1 by s integral e power minus st dt. So basically minus t e power minus st by s minus e power minus st by s square. So if you just take this term and put it here, t e power minus st by s minus e power minus st by s square with the limit 1 to 4, the limit 1 to 4. So immediately you will be getting, put the upper limit and lower limit. So e power minus s 1 by s plus 1 by s square minus e power minus 4s 4 by s minus 1 by s square. This will be the final answer after putting the limits. Okay, so you can verify this. So like this we can proceed to find Laplace transformation of any given function. Now see, whenever you have this type of question, then you have to proceed like this, or whenever you have this type of question, suppose direct, okay, obviously these things will not be given, but in the question you will find, you need to apply these formulas. Okay, so for that separate table we have, that we'll study later on. Okay, now another question I can give you, suppose Laplace transform of t power half. Okay, if I give this question, find Laplace transform of this one. So you can try this question. Already you got that formula, Laplace transform of t power b. It is what? Gamma b plus 1 by s power b plus 1. Okay, so we had this formula earlier, so we'll apply this. So as per this formula, half plus 1 by s power half plus 1. So what will be this? Half plus 1. So you know this formula, half gamma half s power 3 by 2. This is the formula already you had in calculus course. Gamma, suppose b plus 1 I am writing, so b into gamma b. Okay, this is the formula. So half, gamma half means root over pi, and here you have s power 3 by 2. So this will be the answer. Okay, so here two results we are using. Gamma half means root over pi. Okay, these are few results we are using. Now like this you have plenty of question and you can try these questions for Laplace transformation. Now we'll see sufficient condition. Now next part, it is very important, sufficient condition for Laplace transformation. Sufficient conditions for Laplace transformation of the function ft. What are the sufficient conditions? Okay, so first sufficient condition for, or first condition is, the function ft is piecewise continuous. The function piecewise is or in other words you can say sectionally continuous. Okay, and if the function is piecewise continuous, then okay, we can proceed with the Laplace transformation. Okay, then the second criteria is ft is of exponential order. It is of exponential order. Okay, of suppose exponential order of gamma. Okay, or in other words, if I just want to say what is exponential order of gamma, That is, what is the meaning of exponential order? First you need to know. That means there exist, that is, there exist m and gamma such that basically that kernel part, okay, it should be ft less than m e power gamma t, okay. Such that this one, okay. So basic idea is that the function it is of exponential order of gamma, means it is the function, it is not growing faster than e power gamma t, okay. So this is one of the conditions, so that the improper integral exists, okay. Improper integral exists. See the first condition, what we said, provided the integral exists. This was the first statement. So integral exists means basically this function, it should be of exponential order, okay, then only the integral can exist. Now see, this is the condition for sufficient condition for Laplace transformation. Now see, note this thing, these two conditions are not necessary, not necessary conditions, okay. So these are sufficient but not necessary conditions. Now there are few properties of Laplace transformation. See, sufficient conditions, you should know that whether this Laplace transformation has some sufficient conditions or not, okay, in which case this Laplace transformation exists or not, okay, this thing you should know. Now few important properties, general properties of Laplace transformation we have, okay. So we'll see one by one all those properties. So few important properties of Laplace transformation. Important properties of Laplace transformation. Laplace transform. Few important properties. So first important property is linearity. Linearity property. Linearity property says that if Laplace transform of suppose I am writing c1 f of t plus c2 g of t, that immediately implies c1 Laplace transform of ft plus c2 Laplace transform of gt, okay. This is Laplace transform and the linearity property, okay. Now second property it is, first let me write down these few properties, and after that we'll solve question. That time the ideas will get more clear to you, okay. And then the second one it is first shifting theorem, first shifting theorem or first shifting property. It says that suppose if Laplace transform of ft is suppose fs, okay, then Laplace transform of e power at ft, it is given by Laplace transform of that, see previously it was fs, so immediately what will have, see Laplace transform of e power at means f of s minus a, okay. This is the first shifting theorem. This is very important and it is frequently applicable in practice, so here you can make a note of this, okay. This is called first shifting theorem. Just see, e power at it is in multiplied form, so So immediately f of s minus a. This is first shifting theorem.